Hello, thank you for joining our talk. My name is Raúl, and here we have my colleague Victor. We're both software engineers at SUSE Rancher, and today we're going to talk about how to enforce a secure supply chain on Kubernetes. Attacks can happen at every link in a typical software supply chain. We took this threat model from the SALSA security framework. SALSA, or Supply Chain Levels for Software Artifacts, it's a security framework. It's a checklist of standards and controls to prevent tampering, improve integrity, and secure packages and infrastructure in our projects. So if you're using Kubernetes, a typical software supply chain might look like you obviously have some source code. You're probably using some version control such as Git. You might have a build system, some build pipelines that fetches this source code alongside its dependencies, compile it, run some tests. If the tests are successful, it creates some artifacts or container images, and then it pushes these container images to an OCI registry. So later, in our production Kubernetes cluster, we will pull these container images. There are many places when things can go wrong in this supply chain. If you look at this picture, all of these letters, they're all real. There are real world examples of attacks that happen in the SALSA website. If we start looking from the left-hand side, first thing we need to make sure is the source integrity. We need to secure our source code. Imagine someone get access to our Git. They can push malicious code. It will trigger a new build. It will compile into a new artifact, which is a container image, and then our Kubernetes cluster can pull this malicious container image, and that's it. We're running some malicious code in our production environment. And then we have the build integrity. We need to make sure that what we are building from our source code, it's what we actually see in our production environment. Just imagine someone gets access to our OCI registry and pushes an image that contains some malicious code. We don't notice, and then we start pulling this image from our production Kubernetes cluster. That's it again. We already are running malicious code in our Kubernetes cluster, and that's what we're going to learn today, how to prevent that from happening. But today, let's look at two of the examples SALSA security framework provides for this threat. First one, it's an attack that happened to a company called CodeCop. Someone got access to a leaked credential and managed to upload a malicious artifact to a Google Cloud bucket. Then users started downloading this malicious artifact, and they didn't know it was malicious. They didn't know it didn't came from CodeCop. How they could have fixed it? By providing some provenance check for this artifact. And then we have the attacks that happen on package mirrors. Someone started running mirrors of several popular package repositories, and they could have been used to serve malicious package, and the same. Users could not verify at this point that they were not trusted packages. So similar to the previous example, provenance check of these artifacts could have prevented this problem, this attack. So what do we want to do? What are we going to learn today? We are going to learn how to sign our container image and how to verify them. So we can make sure that what we are building in our pipelines, it's what we really see in our production cluster, and no one has changed anything. And for that, let me introduce Sisto. Sisto, it's a combination of open source technologies that allow us to handle signing, verification, and provenance checks. With Sisto, we can sign many things, not just container images. They also support binary blocks and anything that can be stored in an OCI registry, such as WebAssembly modules, Helm charts. Sisto is seeing a lot of adoption. It's growing by the day, especially in the open source community. Even Kubernetes itself has started signing all the artifacts with Sisto, starting on version 124. So let's see some of the tools that Sisto provides. The first one I'd like to talk about is cosign. It's the tool we actually use for the actual signing and verification of the container images. When you sign an image, the signature is stored in an OCI registry. You can use your PKI if you already have one. If not, cosign allows you to create keeper and everything. It also has support for KMS. If you are using AWS KMS, Google Cloud, or HashiCorp Vault, you can integrate the keys you create with cosign in this key management system. And it also supports hardware signing if you have one of them. So let's see how you can sign using cosign and a keeper. First thing we need to do is to create a keeper. And for that, we type cosign generate keeper. We need to provide a password for the private key, and then it creates a private key and a public key. We need to keep the password and the private key someplace safe. That's very important. If someone gets access to them, then they can sign on our behalf. And then for the actual signature, we just need to pass the private key, and the name of the container, and that's it. And as you can see here, it's pushing the signature to the OCI registry. So the signature is stored in the OCI registry. So in order to verify signatures, what we need to do is to provide the public key we generated in the previous step. We just type cosign, verify the public key and the OCI registry. And that's it. So this is the traditional way that Sisto provides for signing and verification, which involves handling keys. You need to make sure your private key and the password doesn't get compromised. You need to distribute the public key. But there is an additional way of signing, which is called keyless. We will talk about keyless signing a bit later, but now let me introduce to other tools from the Sisto project. So Fulcio. Fulcio, it's a code signing certificate authority. It's built to make shortlist certificate available to anyone. This certificate, they don't live for more than 20 minutes. It issues certificate based on an OIDC email address. OIDC, or OpenID Connect, is an identity layer built on top of OAuth 2. It allows third-party applications to verify the identity of the end user. So once Fulcio issues a certificate, it will store it in a certificate transparency log. The Sisto community provides a public instance for Fulcio. It's still experimental. Okay, so another tool that Sisto provides is Record. Record is a transparency log. It's an immutable tamper-resistant ledger of metadata, which means that it's a ledger where we can create new records, but we cannot modify or delete existing records. They provide some APIs for validation, so we can query the data inside of this ledger. They even provide a CLI if we want to use it for querying the data. Same as Fulcio, they provide a public instance, but still experimental at this moment. So let's put everything together. If we take cosign, Fulcio, and Record, we can sign using the keyless mode. So let's see how that looks. Keyless mode use an OIDC token for identity. So when you try to sign with keyless, first thing you need to do is to get an OIDC token from your authorization server. Once you get it, you pass it to Fulcio. Fulcio will verify your identity based on this token and the email. It will issue some certificates. You will use these certificates for the actual signing. And then the signature will be stored in the record transparency log. So anyone can verify the transparency log to verify that the signature is valid. It has support for automated environments such as CI/CD pipelines. We will see an example later. Let's see a bit more about this keyless workflow. Okay, so let's start with the developers. We're the developers and we want to sign an artifact. First thing we need to do is to request a certificate to our OIDC authorization server. We authenticate, we get back a token, we pass this token to Fulcio. Then Fulcio will store the signing certificate in the record transparency log and it will give us back this certificate. Then we use this certificate for the actual signing. That's it. That's it. We have our artifact signed. And what about verification? The end user wants to verify the signature. Okay, it will find and download the artifacts. It will check for the signature in the transparency log. And then you just need to check that the signing party is in system trust root. If that's okay, then it can successfully verify the signature. And for monitoring, as everything is stored in the record transparency log, and remember, no one can modify or delete any record here. So that's where you have to look for monitoring. It's just to look into this transparency log. Okay, so now let's look at a real example. Let's see how we can actually do a killer signing using Sixto. Okay. Oh, sorry. So first, let's sign. Okay, we are asked to log in into our OCI OIDC provider. In this case, we're going to choose GitHub. That's it. Authentication was successful. And if we come back here, it has pushed the signature to the OCI registry. And it also created a transparency log entry. So we can even take the CLI record provide and check this entry, which is there. We are using the public instance since we haven't specified any Fulcio or record instance, it will use the public instance by default. So now how we can verify this signature. So we just need to do cosign verify. And that's it. I mean, we can check here the issuer, which was GitHub, and my email. So based on this email, you can trust that it's the developer they are saying they are. So there is no need for public key or anything at all. Okay, this is great, but still, you need to provide, you need to do some manual intervention. That's not great. So how we can integrate this inside of a CI/CD pipeline? They have automatic support for GitHub Actions and Google Cloud, but even if you're using a different environment, they have an identity token flag you can pass to cosign, or you can pass the OIDC token. So let me show you an example. Okay, this is a small app I created for this demo. So if we go to this GitHub action, first thing we see here is it will run on every time we create a tag. The permission, this is quite important. We need to give permission for the ID token. This is the OIDC token. Then we're just compiling the image, that's fine. And then here we install cosign and we do cosign sign and the name of the image, and that's it. We mark it as experimental, but that's it. There is nothing here. There is no key. We are not even saying anything about OIDC. Cosign is smart enough to detect that he's running inside of a GitHub action, so it will fetch the OIDC token from GitHub, and it will sign the image. We can see how this action went for one of the tags I created. Okay, this one, the 041. Yeah, as you can see here, in this step, we created the transparency log, and we pushed the signature. We can even verify that the signature was pushed. Yeah, so this was the tag, and this was the signature that was pushed. And actually, this is the other signature we pushed 3 minutes ago when we were doing this on my terminal. So the signature are stored in the OCR registry, in the GitHub OCR registry, same as we have the actual image. Okay, so now let's verify this signature. It was the tag 041. Okay, so as you can see here now, the issuer is a token.github actions. And then the subject, it's the information about the workflow we were executing this signature. So we can use this information for verification. And we will see later how we can use this inside of a Kubernetes cluster so we can verify this signature. Okay, so let's recap a bit. How we can make sure that the container images we created in our build pipelines are the same that we see in our production Kubernetes cluster. First thing we need to do is we need to sign our artifacts or container images in our CI/CD pipelines. Then we need to verify these signatures. We have to do that inside of Kubernetes using a dynamic admission control. So we make sure that a pod that doesn't contain a verified image doesn't reach our production cluster. With that, I would like to hand over to Victor, who will tell us more about this dynamic admission control.
Thanks, Raúl. So as Raúl was saying, we need to check in our cluster for those signatures and make sure that they are verified correctly. Things are signed and verified. And how do we do that? We do that with a dynamic admission controller. Let's see how that works. So here in this slide, we have a Kubernetes cluster. On the left, we have our happy user or things that hit the API server, could be CI/CD and so on. And in the center, we have this big blue box, which is the API server. We can see that it exposes some webhooks. And once things have gone through the different phases of the API server, they get persisted in etcd, which then changes the cluster to whatever state we want to have it with the resources that we want. Let's put an example. Let's say that our user on the left wants to create a pod. And we want to ensure that in our cluster, all the pods have an annotation prod. So here we have an example, no? And let's see how that works and how does it look like going through the phases. The user does a control apply and we get the JSON request, which is just a JSON. The request would go through the authentication and authorization phase, which succeeds, and then we go to the mutating admission phase, where we have the webhooks. And in those webhooks, we can just connect our logic. And in this case, it would mean that we take the JSON of the pod, which is just containing the spec of the pod, and we add a line with annotation prod. That's it. We have mutated the request, which then goes to the next phase, which is the schema validation one, where we just check the JSON, so it complies with the schema of the pod, which is no problem, and then goes to the next phase, which is the validating admission one. Then we have the webhooks again, where we connect to our logic, and here we just check the pod, that the JSON of the pod contains the annotation prod. If it has that annotation prod, then we accept that request, and if not, we reject that request. In this case, we have mutated the request already, so it contains the annotation prod line. So we accept it, which means that it goes to etcd, gets persisted there, gets taken by the control plane of Kubernetes, and then the pod is going to get created at some point. That's it. So with dynamic admission controllers and the webhook that the Kubernetes API provides us, we can enforce things in the Kubernetes resources. Let's go with a concrete example then. For this example, we're going to use Kubernetes, which is a CNCF project that my colleague and I are involved with, so we are quite acquainted with it, and it has some properties that simplify this signature and things. So as a normal policy engine of Kubernetes, it monitors and enforces policies, and it validates or mutates requests, as we have seen. It gets installed via Helm charts, as many things in the community, and it provides 3 CRDs. It provides a CRD for policy servers, how to configure Kubernetes itself, and it provides 2 CRDs for the policies, admission policies or cluster admission policies, which are cluster-wide. The policy server and the libraries of Kubernetes are written in Rust, which means that for Sigstore there was no library written in Rust, so we implemented a Sigstore Rust library. You can see the link there. We are happy that we sent it upstream and it has taken a life of its own there. And the policies of Kubernetes, they are WASM modules. They are WASM binaries, which means that every language that compiles to WASM can be used as a policy. In this case, for example, Kubernetes provides SDKs for Rust, Go, Swift, TypeScript, Rigo, and OPA policies, and so on. You can just write your own SDK with the things that we provide if we don't support your language yet. And why this is important, we're going to see. This will simplify things in the future for signatures. So talking about WASM, for those that don't know about WASM, let's talk about what it is. WASM is small. It's a binary instruction format. It's a common target architecture that languages and compilers can target, and it provides binaries that are super small. For example, the policies that we normally do are 3 megabytes, 1.5, things like that, super small, which is nice for moving around in clusters and registries. It's polyglot. As we had said, everything that can compile to WASM can be used. So we have a lot of languages that already compile to WASM and more are getting added day to day. It's secure. It's a sandbox runtime that is isolated. It comes from the web ecosystem and it uses a defined list of APIs that can escape the sandbox. And it has memory safety, control flow integrity, things that are super nice. And it's portable because once you compile it, you have the binary and you can run it everywhere that you want. You can run it also outside of the cluster, in this case for the policies. All this means that you can just leverage whatever language knowledge that you have. Maybe you are used to writing your things in Go, then use Go, use your knowledge of Go, the libraries of Go, the CI/CD that you have set up for your things, Git, and so on. So you can tap into all those things and they come for free, so to speak. The WASM binaries, the WASM modules, are distributed in OCI registries. Why? Because they are a first-class citizen in OCI registries at the same level as container images in the registry or Helm charts in the registry, which is super nice and simplifies signature and verification. And with that said, let's look on how to secure the cluster. How do we do that? Okay, for that we need to first ensure that all the policies are signed and verified. How do we do that for Kubernetes policies? They are WASM modules that are supported in OCI registries, so it's just the same as container images. My colleague Raúl has explained how to do assigning and verification of container images. The same happens for Kubernetes policies. A cosign sign or a cosign verify will work with contain these Kubernetes policies. Here, for example, we see a cosign verify of a policy, and we see that it verifies and it prints the issuer and subject. In this case, for this policy, it looks like it has been signed using a GitHub Actions workflow, and the subject informs us of which repo contained that workflow. And given that they are WASM policies, and they can be run outside of the cluster, then they can also be verified outside of the cluster. It's just something that is in the registry, so you just do a verify. In this case, you can use KWCTL, which is our tooling also, and you can verify that policy outside of the cluster. Policies are obtained from either the hub.kubernetes.io that we provide, where we have a list of policies there, and we have the policies created by the Kubernetes team. And for those that are signed, via Sigstore, you can see a little tick. But you can also find Kubernetes policies in artifacthub.io. Given that Kubernetes is a CNCF project, you can have the Kubernetes policies there, and they will be having that tick. It's not there yet, but this is fairly new. And you can also publish your own if you want, which is nice, and we encourage you to do. Okay, now we know how Kubernetes policies look like, no, for signing and verifying. How do we enforce that in the cluster? How do we configure Kubernetes for that? Well, we provide a default configuration, and that default configuration will be set up. You need to set it up for the policy server, and that's it. How to find that default configuration? You can use the tooling that we provide, KWCTL, to create that default config, and here we see it. You can see it has a kind GitHub action, which means things that have been signed in GitHub Actions, and then an owner, in this case is the org Kubernetes, and then a repo. Which what this means is that everything that has been signed via GitHub Actions coming from the Kubernetes organization would be by default trusted. And of course, you can add more entries here if you want to verify more policies. You can also use different kinds. Maybe you want to use a public key and private key. It's all there. We encourage you to look into the verification config. And once we have this set up in the policy server, we ensure that all policies are trusted. But now we need to ensure that all workloads in the cluster are trusted, are signed and verified. And how do we deploy workflows in a cluster? By using workload resources. That means deployments, jobs, replica sets, and so on, pods, and so on. Everything that can contain container images in their spec. And for that, we use a policy that will enforce that those container images are signed. So here we have an example of a policy. This is a policy that the Kubernetes team has written. It's written in Rust. So we have used the Rust SDK that we provide for that. It's 200 lines of Rust implementation and maybe 400 or so of tests, which is important in these cases. And if you would prefer to not use this policy, you can just implement your own with the SDKs that we provide. No problem with that. So how does this policy work? Let's say that a user now wants to instantiate a pod. A pod inside has init containers or ephemeral containers. Can have in the spec any of those. So this policy checks for those and checks if those container images that are listed there with the tag have signatures associated to that tag. And if that signature is correctly verified and trusted by the settings of the policy, that's it. If the container image is not signed or it's not trusted, that signature is not trusted, then that pod would get rejected. If all the container images in that pod are trusted, which means they are signed by somebody that we trust, then we could approve it. That's it. We are done. But no, we are not done because container image tags are mutable. You can always do an app example version 1.0, no, a container image, but then you can push again the app example 1.0 again, overwriting it, which is not nice. And that poses a security problem. So what we need to do is get that JSON request with the pod and mutate that JSON request. And we would append the checksum digest of that container image tag. So then we are appending the digest with the checksum and we are pinning exactly which container image tag we want to use. And then we can approve it. This is good because it's a best practice that we should follow. And it's something that we should have in mind. Okay, here is the example of the cluster admission policy in code. Here we're defining the resource for the cluster admission policy. And we can see that the spec.module is this verify image signatures that we have talked. And then we are defining the rules, in this case for create and update operations of pods. So this policy is going to check all the pods, create and update operations. We are defining that we want it to mutate things. So it appends the checksum digest. And then we have the settings of the policy. In these settings, we are looking for all the images that are inside of pods. And we want them to be signed via GitHub Actions with the owner Bigquad, the org Bigquad, and coming from the repo app example. That means that the GitHub Actions workflow would have been run in a job that comes from this repo. We could use different, instead of using the asterisk for the image, we could use the GitHub registry slash Bigquad, and then all the things that come from that namespace in the GitHub registry would be needed to be signed by the owner Bigquad and so on. The repo is optional, so we could just leave it out. This is also a best practice. I don't know if you remember that we have been talking about issuer and subject, but it's not here. This is because as GitHub Actions has done for the IDC token, the issuer and subject of the ICD token in GitHub Actions informs of the repo that contains the code for the workflow, but not the repo that is running the job. That's in an extension of the certificate, of the X502 certificate of the OIDC. So we should check that. And we are doing that in this case with the logic of this policy, and this is a best practice. So we encourage everybody to use these kind of things and not go directly for issuer subject, and be aware of those things. Okay, we instantiate this policy. Once the status of this policy, as we can see bottom right, is status active, we are enforcing it in the cluster. That means that the cluster has been made secure for all workloads. What happens if we try to instantiate a pod that has not been signed? Let's see how that looks. Here we have a pod, and the pod has a container. The image of the container is nginx, which we know it's not signed via Sigstore yet. And we can see what happens. It just rejects the pod. And it says pod nginx is not accepted, verification of image failed, no signatures found for image, what we wanted. Perfect. And how does it look when the image is signed? Here we have it. It's the same, but now we are using a pod that has a container image that is signed. So we just do kubectl apply and it works. That's it. We need to remind ourselves that we set it to be mutating. So now we do a kubectl get pods of that unsigned pod and look for the container image, we can see that it has appended the checksum digest. We can see the at and then SHA-256, and it goes with the checksum digest, which means that that container image tag has been pinned, which is what we wanted. So good. Now we have secured everything in that aspect. So what's next? Okay, we have made sure that the policies are signed and verified, and we have made sure that the workloads that we have created are signed and verified. But we have a lot of dependencies also, maybe, maybe some things that we consume from the community. We could just sign those again, re-sign them. But a better way to do it would be to use software bill of materials, which is a list of our dependencies that we can just sign and verify in a different way. This falls out of the scope of this session because it is a quite complex topic, and we look forward to talk about that in the future. And once we have that, we will have secured the cluster. What we need to do as a community is to sign and verify everything. Everybody depends on something, so it would greatly improve the strength of the community if we can sign and verify everything via Sigstore. And what's next for Kubernetes in the Sigstore topic? Well, we want to expand CI integration. For example, we have shown how to do best practices for GitHub Actions, and we look forward for Sigstore integration in GitLab and other CI tools, which are not there yet. They need to set their OIDC tokens correctly and so on. And once that's set up, we would be happy to provide best practices for those. And if you like this approach of using Kubernetes for securing your workloads in the cluster, please try it. You can find us there in the website, kubernetes.io. You can find our policies in artifacthub.io and the hub.kubernetes.io that would be migrated to artifacthub.io. We are on GitHub, and you can talk to us in the Kubernetes channel, in the Kubernetes workspace of Slack, and in Twitter. And with that said, many thanks for joining us. We hope that you have enjoyed this session.